Humanity has always looked up at the stars and wondered what lies beyond. For centuries, the dream of reaching another solar system has lived in our myths, our science, and our deepest imaginations. But what if that dream isn't as far off as we think? What if, hidden in the equations of physics and the blueprints of engineers, there are real pathways to the stars waiting to be uncovered? Today, we're diving into 30 breathtaking theories about how the universe's first interstellar travelers might finally breach the cosmic horizon. Some are grounded in cutting-edge science, others feel like they're pulled straight from science fiction, but all of them could hold the key to humanity's greatest leap. Picture this, a spacecraft not much larger than a postage stamp, propelled by lasers to a fraction of the speed of light, or a generational ship where entire families live and die during the centuries-long journey to a distant star. Maybe the answer lies in bending space itself, creating shortcuts through the fabric of reality. These aren't just wild guesses, they're serious proposals from some of the brightest minds on Earth, each one a potential blueprint for our future among the stars. And yet, for every theory that feels within reach, there are others that challenge everything we think we know about physics, time, and the very nature of exploration. This is more than just a list of ideas, it's a map of possibilities, a glimpse into the audacious ways humanity might one day slip the bonds of our solar system. Some of these theories could become reality within our lifetimes, others might remain dreams for centuries, but each one tells us something profound about our place in the cosmos and the boundless curiosity that drives us forward. So buckle up, by the time we're done, you'll never look at the night sky the same way again. What if humanity isn't the first civilization to reach for the stars? The ancient alien hypothesis suggests that long before humans even walked the Earth, other beings might have already mastered interstellar travel. This idea isn't just wild speculation, it's rooted in strange cosmic signals, baffling interstellar visitors and artifacts that defy easy explanation. Take the WOW signal, a radio burst detected in 1977 that lasted just 72 seconds. It came from deep space, matched no known natural phenomenon, and has never been repeated. Some scientists argue it could have been a stray transmission from an advanced civilization. Then there's Oumuamua, the mysterious object that zipped through our solar system in 2017. Its unusual shape, lack of a comet-like tail, and unexpected acceleration sparked theories it might be an alien probe or even a derelict spacecraft. The real puzzle is the Fermi paradox. If the universe is so vast and old, why haven't we found clear evidence of other intelligent life? One answer might be time. Civilizations could rise and fall over millions of years, leaving only fleeting traces like echoes in the dark. Ancient alien theorists point to Earth's own unexplained artifacts, like the Antikythera mechanism, a 2,000-year-old device with gears precise enough to track celestial movements. Could it be a remnant of lost knowledge, or even a gift from starfaring visitors? Others argue that advanced civilizations might simply be unrecognizable to us. Their technology could bend space-time, communicate in ways we can't detect, or exist in dimensions beyond our perception. Skeptics say these are just gaps in our understanding, not proof of aliens. But the possibility remains tantalizing. What if we're not pioneers, but latecomers to a galactic neighborhood where others have already come and gone? The universe is billions of years older than Earth, plenty of time for civilizations to blaze across the cosmos, leave their mark, and vanish like footprints in cosmic dust. What if crossing the vast emptiness between stars wasn't about speed or endurance, but about bending the very fabric of space-time? Enter wormholes, the universe's hypothetical shortcuts. These cosmic tunnels, known in physics as Einstein-Rosen bridges, emerge straight from the equations of general relativity. Picture space as a crumpled sheet of paper. Normally, traveling from one side to the other means covering the entire length. But if you could fold the sheet so two distant points touch, piercing through creates a bridge, a wormhole, turning a journey of light years into a stroll across the threshold. The math checks out, but the reality is far trickier. Natural wormholes, if they exist at all, would likely be microscopic, unstable, and collapse instantly under their own gravity. The key to making them usable: exotic matter, a theoretical substance with negative energy that could prop a wormhole open long enough for traversal. Think of it like scaffolding holding up a tunnel through a mountain, preventing it from crumbling mid-passage. The catch: we've never observed exotic matter, and producing it would require technology far beyond our current grasp. Science fiction has long flirted with this idea. Films like Interstellar depict wormholes as shimmering, spherical gateways, a poetic interpretation, but one grounded in real science. Kip Thorne, the astrophysicist who advised the film, worked backward from the script's needs to ensure the portrayal stayed within relativistic plausibility. Yet even he admits the challenges. Navigating a wormhole without being ripped apart by tidal forces or random quantum fluctuations would require precision bordering on magic. But what if wormholes aren't just cosmic flukes? Some theories suggest advanced civilizations could engineer them artificially, stitching space-time like master tailors. Others propose they might be relics of the early universe, frozen in place during the Big Bang's frenzy. Either way, the implications are staggering. A stable wormhole network would render galactic travel as routine as subway commutes, linking civilizations across the cosmos. Until then, these elusive bridges remain the ultimate what if, a tantalizing reminder that the universe's rulebook might still have pages we haven't turned. Imagine setting off on a journey so long that your great-great-grandchildren would be the ones to finally reach the destination. This is the core idea behind Generation Ship's massive, self-sustaining arcs designed to carry entire communities across the unimaginable gulfs between stars. Unlike sleek, fast-paced sci-fi vessels, these would be more like floating cities where families live out their lives tending crops, maintaining systems, and raising children who will inherit the mission. The concept isn't new. In 1929, scientist John Desmond Bernal first envisioned world ships, colossal habitats housing thousands, but the challenges are as vast as the distances they'd crossed. Sustainability is the first hurdle. A closed ecosystem must perfectly balance oxygen, food, and waste recycling for centuries. One crack in the system, one failed harvest, and the entire mission collapses. Experiments like Biosphere 2 in the early 90s showed just how fragile artificial environments can be. Oxygen levels dropped dangerously, crops failed, and crew morale plummeted. Now scale that to generations. Social dynamics add another layer. How do you maintain stability when dissent, cultural drift, or even rebellion could doom everyone? Sociologists speculate about strict hierarchies, rotating leadership, or even AI governance, but history shows human societies rarely stay static. Then there's the ethical weight of binding unborn generations to a mission they didn't choose. Is it fair to raise children who'll never walk under an open sky, whose sole purpose is maintaining a ship until it reaches a world they might never see colonized? Some argue it's no different than earthbound societies passing down cultural legacies. Others call it a form of cosmic tyranny. Yet, for all the obstacles, Generation Ships might be our most realistic shot. They don't require breakthroughs in physics, just endurance, planning, and a willingness to think in timescales longer than empires. In a way, they're the ultimate test of humanity's ability to cooperate across centuries. And if they succeed, the descendants who step onto that new world won't just be explorers. They'll be living proof that the human spirit can outlast even the void. Now imagine harnessing the power of light itself to propel a spacecraft across interstellar distances. That's the bold vision behind Breakthrough Starshot, an ambitious initiative to send a fleet of tiny, wafer-thin probes to our nearest stellar neighbor, Alpha Centauri, riding on nothing but laser beams. These aren't traditional rockets with roaring engines. Instead, think of postage stamp-sized chips attached to gossamer-thin sails, pushed to 20% the speed of light by an array of million-watt lasers firing from Earth. At that velocity, a journey that would take tens of thousands of years with conventional propulsion could be slashed to just 20. The physics behind light sails is deceptively simple. Photons, though massless, carry momentum. When they strike a reflective surface, that momentum transfers as a tiny push. Scale it up with a powerful enough laser, and the cumulative effect could accelerate a lightweight craft to staggering speeds. The Starshot design calls for sails just a few atoms thick, made of ultra-reflective materials like graphene or metamaterials. Each nanocraft would weigh mere grams, carrying miniaturized cameras, sensors, and communication equipment, a triumph of nanotechnology. But the challenges are as immense as the ambition. Keeping a laser beam tightly focused over light years is like trying to hit a speeding coin from New York to Los Angeles with a pinpoint of light. Even the slightest vibration or misalignment could send the probe veering off course. Then there's the interstellar medium. Dust grains no larger than a speck could vaporize a sail traveling at such velocities. Engineers propose strategies like redundant probes and self-healing materials, but the margin for error is razor-thin. Funding from visionaries like Yuri Milner has injected life into the project, but skeptics question whether the necessary breakthroughs in laser technology, sail materials, and power generation are achievable within decades. Yet, even partial success could revolutionize space exploration. A scaled-down version might explore our solar system, zipping past Pluto in days rather than years. And if Starshot succeeds, those first grainy images from Alpha Centauri wouldn't just be a scientific triumph. They'd prove that humanity can reach the stars without waiting for physics-defying warp drives or century-long generation ships. Just ingenuity, patience, and the timeless power of light. What if astronauts didn't experience the grueling centuries of interstellar travel at all, but simply slept through them? Cryogenic suspension offers a seductive workaround to the limits of human lifespans, freezing biological activity until arrival at a distant star. The concept has fueled sci-fi for decades, from films like Passengers to Alien, where crews drift in icy slumber while their ships traverse the void. But cryonics isn't just Hollywood fantasy. Real-world organizations like Alka Life Extension Foundation have already preserved hundreds of patients in liquid nitrogen, banking on future science to revive them. The premise seems straightforward. Chill the body to near absolute zero, halting cellular decay, then reanimate it when technology catches up. Yet the reality is a labyrinth of scientific hurdles and moral quandaries. The first challenge is ice, the enemy of cryopreservation. When tissues freeze, jagged ice crystals shred cell membranes like microscopic knives. Modern techniques combat this by replacing blood with cryoprotectants, glass-like chemicals that vitrify organs instead of freezing them. Success has been achieved with tiny structures like rabbit kidneys, which functioned after thawing. But scaling this to an entire human body, that's uncharted territory. Even if cells survive, reawakening a brain with memories intact pushes against the limits of neuroscience. Some researchers speculate nanotechnology could one day repair freezing damage atom by atom, but we're decades, if not centuries, from such precision. Ethics add another layer of frost. Companies like Alka charge hundreds of thousands for preservation, raising questions about equity. Is cryonics a legitimate scientific frontier or a costly gamble on unproven science? Critics compare it to ancient pharaohs entombing treasures for the afterlife, a mix of hope and hubris. Then there's the psychological toll. Imagine waking centuries later, estranged from everyone you knew, in a world where your skills and culture are obsolete. Films often gloss over this disorientation, but historians warn of future shock far worse than any culture clash witnessed in human migration. Yet, for all the obstacles, cryonics embodies a profound defiance of mortality. It's not just about cheating time, it's about stretching humanity's reach beyond the stars without resigning to generation ships or AI proxies. Whether it's the next step in evolution or a high-tech pipe dream, one thing's certain: the quest to pause life itself forces us to confront what it truly means to explore, to endure, and to remain human across the eons. Einstein's theory of relativity holds a mind-bending secret for interstellar travel. Time itself bends to the will of speed. Imagine boarding a ship that accelerates to near light speed. While you'd experience the journey in what feels like a few years, everyone back on Earth would age decades or even centuries in your absence. This isn't science fiction. It's the cold, hard math of time dilation, where velocity warps the very fabric of time. The faster you go, the slower your clock ticks compared to those standing still. Take the famous twin paradox. One twin blasts off on a near light-speed voyage to a star 20 light-years away while the other stays home. For the traveling twin, the trip might take just 10 years thanks to time dilation. But when they return, Earth's twin has aged 40 years, waiting decades for a reunion that felt like a blink to the astronaut. This asymmetry isn't a paradox at all. It's the universe enforcing its rules. Motion through space directly alters your passage through time. The implications for interstellar travel are staggering. A crew traveling at 99% light speed could reach Proxima Centauri in what feels like just over 4 years to them. Back on Earth, though, the mission would have lasted more than 4 years and 3 months. Push that speed even closer to light and the effect magnifies. A journey to the center of our galaxy, 25,000 light-years away, could theoretically feel like a mere 30 years for the crew while civilizations rise and fall on Earth in their absence. But here's the catch: the energy required to reach such speeds is astronomical. Even with perfect efficiency, accelerating a ship to near light demands more fuel than exists on our planet. Some theories propose antimatter engines or cosmic-scale laser pushers, but we're talking about technology that borders on the godlike, and then there's the human cost. Would any explorer willingly leave behind everyone they've ever known, knowing they'd return to a world unrecognizable? Yet time dilation offers something rare in the cosmos, a cheat code for beating the clock. It doesn't shrink the universe's vastness, but it bends the rules just enough to make interstellar travel conceivable within a single human lifespan. The stars might still be distant, but thanks to relativity, they're not forever out of reach. Here's a thought that might keep you up at night. What if the first interstellar travelers aren't living beings at all, but an unstoppable tide of self-replicating machines silently spreading across the galaxy? This is the eerie premise behind von Neumann probes, named after the visionary mathematician John von Neumann, who first theorized machines capable of endlessly copying themselves. Picture a robotic scout landing on a distant asteroid. Instead of just collecting data, it mines raw materials, constructs exact duplicates of itself, and sends those clones onward to repeat the process. Given enough time, a single probe could spawn billions, saturating the Milky Way in a cosmic blink. Geologically speaking, the math is terrifyingly plausible. Even moving at a modest fraction of light speed, a fleet of von Neumann probes could blanket the galaxy in just 500,000 years. That sounds like an eternity, but remember, the universe is nearly 14 billion years old. If even one ancient civilization developed this technology eons ago, their mechanical descendants might already be everywhere. So where are they? The Fermi paradox rears its head again. Some argue we're living in a galactic quiet zone, intentionally avoided. Others suggest the probes might be microscopic or disguised as natural objects, like camouflaged hunters in a cosmic jungle. But not all scenarios spell doom. physicist Freeman Dyson speculated that benevolent probes could act as interstellar librarians, preserving knowledge across the eons. Imagine discovering a silent sentinel on Mars, waiting to share the wisdom of 1 million extinct civilizations. Alternatively, they might operate under strict protocols to avoid contamination, like a galactic prime directive enforcing non-interference. The darker theories, though, are hard to ignore. A malfunctioning or predatory von Neumann swarm could strip planets bare like locusts, converting entire worlds into raw materials for expansion. Science fiction has long mined this fear, from the berserkers in Fred Saberhagen's stories to the reapers of Mass Effect. Even the seemingly innocuous grey goo scenario, where nanoscale replicators reduce everything to sludge, is just a microscopic cousin of the von Neumann nightmare. Yet the most unsettling question isn't whether such probes could exist. It's whether we'd recognize them if they were already here. The Oumuamua mystery taught us how easily an artificial object might slip past our telescopes. And if a probe wanted to remain hidden, wouldn't it design itself to evade detection? Until we comb every comet, scan every asteroid, we're left wondering, are we alone in the universe or merely the last to notice we're not? What if an entire star could be encased in a colossal machine, its energy harvested to power a civilization beyond our wildest imagination? That's the jaw-dropping premise behind Dyson Spheres' hypothetical megastructures proposed by physicist Freeman Dyson in the 1960s. Imagine a vast swarm of orbiting solar panels or a solid shell surrounding a star, capturing every photon of its light to fuel interstellar travel, supercomputers, or even artificial worlds. This isn't just sci-fi speculation. For a civilization advanced enough to reach Kardashev Type 2 status, able to harness the total energy output of their home star, such a feat might be the ultimate power grid. The real-world intrigue exploded in 2015 with the discovery of Tabby's star, officially named KIC 8462852. Astronomers noticed its light dimming in bizarre, irregular patterns, sometimes by as much as 22%. Natural explanations like dust clouds or planetary debris were proposed, but none fully matched the data. The dips were too sharp, too asymmetrical. Could this be the shadow of a partially constructed Dyson sphere, or perhaps a swarm of energy-collecting satellites known as a Dyson swarm passing in front of the star? The scientific community remains divided, but the mystery opened a thrilling window into how we might detect alien engineering on a cosmic scale. Critics argue that megastructures defy material science. A rigid shell around a star would face unimaginable gravitational stresses, orbital instabilities, and the threat of collisions. Even a Dyson swarm, millions of smaller collectors, would require more raw material than exists in most solar systems. But proponents counter with wild yet plausible workarounds. What if a civilization dismantled nearby planets for resources, turning Mercury into trillions of solar satellites? Or used self-repairing nanotechnology to maintain the swarm? The scale is staggering, but so was the idea of landing on the moon before the 20th century. Beyond power, Dyson spheres could solve another interstellar puzzle: waste heat. All that captured energy has to go somewhere, and physicists suggest looking for infrared signatures, the telltale glow of a civilization radiating excess heat into space. Some researchers have already scanned the cosmos for these thermal fingerprints. Though no smoking gun has emerged yet, the implications ripple outward. If even one Dyson sphere exists, it would mean we're not alone, and that some civilizations outlast their planet-bound infancy. It would also hint at a universe where intelligence doesn't just gaze at the stars but dismantles and remakes them. Whether Tabby's star is hiding alien handiwork or just an odd cosmic quirk, the search for megastructures forces us to confront a humbling truth. The universe might not just be stranger than we imagine, it might be stranger than we can imagine. What if a starship light years away could send messages home instantly, defying the universe's speed limit? quantum entanglement, the bizarre phenomenon Einstein called spooky action at a distance, might hold the key. When two particles become entangled, their properties sync instantly, no matter how far apart they are. Change one, and the other reacts immediately, even across galaxies. On paper, this seems like the ultimate interstellar comms system, a fleet of ships carrying entangled particles, allowing real-time updates without agonizing delays. But physics slams the door on this dream with the no-communication theorem. Here's the catch: while entanglement creates a ghostly link, it can't transmit usable information. Observing a particle randomizes its state, meaning you can't control what message gets sent. It's like having a pair of magic coins that always land opposite faces, but you can't choose which one shows heads or tails. Recent experiments, however, are chipping away at the limits. In 2017, Chinese scientists used the Misha satellite to send entangled photons over 1,200 kilometers, proving entanglement survives across staggering distances. Then in 2023, a team at the University of Chicago manipulated entangled qubits in a way that hinted at influencing outcomes faster than light could travel between them. Skeptics argue these are just loopholes, clever exploits of quantum weirdness, not true communication. Yet visionaries like NASA's quantum AI lab are already prototyping entanglement-based networks for future missions, betting that where there's quantum smoke, there might be fire. Imagine the implications if we cracked it. A probe orbiting a distant exoplanet could beam back data to the moment it's collected with no years-long lag. Colonies light years apart could coordinate like neighbors, but the universe rarely gives free lunches. Some physicists warn that faster-than-light communication could shatter causality, creating paradoxes where messages arrive before they're sent. Others propose workarounds like using entanglement not for messaging, but for synchronizing clocks across interstellar distances, creating a universal timekeeping grid. The truth might lie in the middle. Quantum entanglement won't become a cosmic telephone, but it could still revolutionize how we navigate the void. Think of it as the universe's most secure handshake, a way to confirm a signal's integrity, even if we can't control its content. And who knows, maybe one day, buried in the equations, we'll find the loophole that turns spookiness into speech. Until then, the quantum realm keeps its secrets close. The universe isn't just expanding, it's accelerating, pushed apart by a mysterious force we call dark energy. What if we could tap into that cosmic fuel to propel our starships? This isn't just another twist on rocket science, it's a radical reimagining of propulsion itself. Conventional rockets, even the most advanced ion drives, are prisoners of Newton's third law. They push against something to move forward. But dark energy doesn't play by those rules. It's the universe's own throttle, stretching spacetime itself. Harnessing it would mean riding the very fabric of reality, like a surfer catching an endless wave. The numbers are staggering. Dark energy makes up roughly 68% of the universe's total energy content. A single cubic meter of empty space contains infinitesimal traces of it, but scale that up, and you're looking at a power source dwarfing all the stars in the Milky Way. The catch: we don't even know what dark energy is, let alone how to bottle it. Some theories suggest it's a property of spacetime itself, a cosmological constant baked into the universe. Others propose it's a dynamic field, like an invisible ocean with currents we could someday navigate. Until we crack that mystery, dark energy propulsion remains a tantalizing what if. Compare that to the brutal math of conventional spaceflight. Just to reach Mars, chemical rockets burn thousands of tons of fuel, most of which is spent escaping Earth's gravity. Even nuclear thermal propulsion, which could slash travel times to the outer solar system, relies on brute force physics we've understood for decades. Dark energy offers something radically different, a way to sidestep the tyranny of mass and fuel entirely. Imagine a ship that doesn't push against the cosmos but unfolds it, compressing spacetime ahead while stretching it behind. No exhaust plume, no deafening roar, just silent, seamless acceleration. The closest we've come to this vision is the Alcubierre warp drive, a theoretical design that bends spacetime to create a warp bubble. But while Alcubierre's math checks out, it requires exotic matter with negative energy, another mystery we've yet to solve. Dark energy could be the missing piece. If it turns out to have negative pressure properties, it might naturally warp spacetime in ways we could exploit. Skeptics argue this is all speculative physics, no closer to reality than alchemy was to chemistry. Yet history shows that today's magic often becomes tomorrow's engineering. The real breakthrough might come from spotting dark energy's fingerprints in lab experiments or unlocking its secrets through particle accelerators. And if we ever do, the stars wouldn't just be within reach, they'd be next door. Black holes aren't just cosmic destroyers, they could be the ultimate gravity slingshots, flinging starships across the galaxy at unimaginable speeds. Picture this, a spacecraft skims just outside the event horizon of a supermassive black hole like Sagittarius A, stealing a fraction of its gravitational energy to catapult forward. The concept, known as the Penrose process, is like a thief grabbing a spinning merry-go-round's momentum to launch themselves forward, except here, the merry-go-round is a singularity spinning near light speed, and the payoff is a velocity boost that defies conventional propulsion. The physics is as elegant as it is dangerous. As a black hole rotates, it drags spacetime around it like a whirlpool. Fly close enough, and you can exploit this frame-dragging effect to gain energy, literally robbing the black hole of a tiny bit of its spin. Simulations suggest a perfectly timed maneuver could yield a 20% speed increase, turning a centuries-long journey into a matter of decades. But precision is everything. Venture too close and tidal forces will stretch your ship and crew into atom-thin strands in a process gruesomely dubbed spaghettification. The margin for error, less than a fraction of a percent. Real-world routes might target supermassive black holes which have gentler tidal forces than their smaller counterparts. Sagittarius A, at the Milky Way's heart, is a prime candidate. Its immense size means the spaghettification zone lies far inside the event horizon, leaving a narrow but survivable corridor for slingshot maneuvers. Yet even here, threats lurk. Accretion disk superheated plasma swirling around the hole could fry sensors or shred hulls with particle storms fiercer than any solar flare. And then there's the navigation nightmare. The black hole's gravity bends light so severely that multiple images of the same star might appear, making celestial navigation a hall of mirrors puzzle. Science fiction has flirted with this idea for decades. Interstellar's iconic Gargantua sequence showed the Endurance crew skimming a black hole's edge, their clocks ticking slower than Earth's, a dramatization of real relativistic effects. But the film glossed over the grittiest challenges. In reality, surviving the maneuver would require materials that don't yet exist: shields to deflect lethal radiation, quantum computers to recalculate trajectories in real time as spacetime warps unpredictably, and engines capable of microsecond adjustments to avoid the abyss. The payoff, though, could rewrite the rules of exploration. A successful black hole slingshot wouldn't just offer speed, it'd be a masterclass in harnessing the universe's most extreme phenomena. It turns the cosmos's greatest monsters into tools, proving that even in the face of oblivion, ingenuity might find a way to steal fire from the gods. What if the key to interstellar travel isn't better engines or faster ships, but rewriting life itself? The next frontier might not be mechanical, but biological. Imagine astronauts genetically modified to resist cosmic radiation, thrive in zero gravity, or even slow their aging to endure centuries-long journeys. Scientists are already laying the groundwork, borrowing tricks from nature's toughest survivors. Take tardigrades, microscopic water bears that can withstand the vacuum of space, lethal radiation doses, and temperatures near absolute zero. Their secret, unique proteins that shield DNA like molecular body armor. Researchers have spliced these genes into human cells in labs, dramatically boosting their radiation resistance. Combine that with CRISPR gene editing technology, and suddenly, engineering a post-human starfarer doesn't seem so far-fetched, but radiation is just the start. Prolonged weightlessness wreaks havoc on the human body, muscles atrophy, bones weaken, and vision blurs as fluid pools in the skull. Genetic tweaks could counter these effects. One experiment with mice on the International Space Station showed that suppressing the protein myostatin preserved muscle mass in microgravity. Extend that logic to humans, and you might design astronauts who don't just survive zero-G but flourish in it. Then there's aging. Telomeres, the protective caps on our chromosomes, shorten with time, leading to cellular decay. But certain marine species, like the immortal jellyfish, can reset their biological clocks indefinitely. Harnessing similar mechanisms could stretch a crew's lifespan to match the scale of interstellar travel. The ethical dilemmas, though, loom as large as the scientific ones. Is it right to alter human DNA for a mission, potentially creating a new subspecies of space-adapted people? Philosophers warn of a slippery slope where enhancements lead to inequality, cosmic explorers versus earthbound baselines. And what happens if these modifications are irreversible? A crew engineered for Alpha Centauri might find they can no longer breathe Earth's air or endure its gravity, stranded between worlds like mythological giants. Yet the potential is too staggering to ignore. A genetically optimized crew could travel lighter, needing fewer radiation shields or artificial gravity systems. Their bodies might recycle waste more efficiently or enter suspended animation without cryonics. Some theorists even speculate about synthetic biology designing organisms from scratch to terraform planets ahead of human arrival. Picture algae engineered to photosynthesize under the dim light of a red dwarf, seeding distant worlds with breathable air before we ever land. The line between science and science fiction blurs here. But the lesson is clear. If we're to become an interstellar species, we might need to stop asking how to adapt ships to space and start asking how to adapt ourselves. What if the fastest way to reach another star wasn't through our universe at all, but by slipping into a parallel one where the rules of physics let you cheat? This mind-bending idea springs from multiverse theories, which suggest our cosmos might be just one bubble in an infinite froth of universes, each with its own unique laws. Picture a reality where light speed isn't a barrier, where distances between stars fold like origami, or where time flows backward. For interstellar travelers, these alternate dimensions could be cosmic shortcuts, twisting the very definition of impossible. String theory fuels this speculation. At its core, it proposes that reality isn't made of point-like particles but vibrating strings, humming across 11 dimensions, most curled up too small to see. Some versions of the theory suggest these hidden dimensions could harbor alternate universes, separated from ours by membranes thinner than a quark. The holographic principle adds another layer, implying our three-dimensional universe might be a projection from a two-dimensional surface at its edge, like a cosmic mirage. If true, tampering with that underlying code could rewrite the rules locally, creating temporary wormholes or warping spacetime in ways Einstein never envisioned. Science fiction has danced with these concepts for decades. Doctor Who's Time Lords hop between dimensions through cracks in reality. Rick and Morty's portal gun accesses infinite timelines. But real-world physicists take a more measured approach. Nobel laureate Gerard T. Hooft has speculated that quantum information might leak between universes, offering faint trails for the bold to follow. Meanwhile, experiments with quantum tunneling where particles vanish and reappear past barriers hint that reality might be far more porous than we think. The catch, even if alternate universes exist, crossing into one demands energy densities akin to the Big Bang. Some theories propose focusing lasers to microscopic points, creating tiny fractures in spacetime. Others imagine harnessing dark energy to inflate a new bubble universe adjacent to ours, then tunneling through. The risks are as staggering as the rewards. A misstep could strand travelers in a dimension where atoms can't form, or worse, unleash forces that unravel our own universe like a loose thread, yet the allure persists. If even one navigable parallel exists, the cosmos becomes not a vast desert but a crowded metropolis, with back alleys and side streets leading to destinations beyond our wildest maps. Until then, multiverse hopping remains the ultimate high-stakes gamble, where the price of failure is oblivion, but the payoff is rewriting the destiny of life itself. Imagine a cloud of microscopic machines, each no larger than a dust mote, venturing into the void ahead of human explorers. These aren't passive probes but tireless builders, programmed to transform barren worlds into welcoming homes long before the first colonists arrive. This is the revolutionary vision behind nanobot swarm colonization, where the pioneers of interstellar expansion aren't flesh and blood, but trillions of self-replicating robots working in concert like a cosmic ant colony. NASA Jet Propulsion Laboratory has already taken the first steps toward this future with projects like the Shapeshifter, a fleet of small, modular robots that can combine into larger structures or split apart to explore treacherous terrain. Picture a version of this technology scaled down to the nanoscale, where each unit carries solar-powered molecular assemblers capable of rearranging raw asteroid material into breathable air, radiation shielding, or even entire habitats atom by atom. The strategy hinges on exponential growth. A single seed pod lands on a distant world, extracts local resources, and spawns millions of copies within weeks. Those copies then fan out, building landing pads for human ships, synthesizing food from atmospheric gases, or sculpting underground cities safe from cosmic rays. The real game changer lies in redundancy. A traditional mission risks total failure if one critical system breaks, but a nanobot swarm has no single point of failure. Damage 1,000 units and millions more step in. Lose a construction site to a dust storm, and adjacent swarms reroute materials to compensate. This resilience mirrors nature's most successful strategies. Think of how a coral reef thrives through countless tiny organisms collaborating without centralized control. Yet the challenges loom as large as the potential. Powering nanobots over interstellar distances would require breakthroughs in energy efficiency, perhaps borrowing from bioluminescent organisms or ambient radiation harvesting. Communication between swarm members demands fault-tolerant networks that won't fail when a solar flare scrambles signals. And then there's the specter of mutation. What happens if a replicating error creates a rogue swarm that consumes materials indiscriminately? Science fiction nightmares like the Grey Goo scenario remind us that exponential growth cuts both ways. But if we crack these puzzles, the payoff redefines exploration. Instead of hauling prefab habitats across light years, we'd send a single canister of nanobots with the instruction, build a city. They could sculpt domes from Martian regolith, weave space elevators from carbon nanotubes, or even bioengineer lichen to seed alien atmospheres with oxygen. The visionaries at institutions like the Breakthrough Initiatives speculate that such swarms might already be out there, evidence of past civilizations that mastered this technology and left silent architects waiting among the stars. Perhaps the most profound implication isn't logistical but philosophical. If nanobots can prepare worlds for us, are we still explorers or inheritors? The line between discovery and creation blurs when your footsteps follow paths laid down by machines you sent centuries earlier. One thing's certain, in this version of the future, the universe doesn't just belong to those who cross the void, but to those who teach the void itself to welcome them. What if the key to reaching the stars wasn't transporting fragile human bodies, but beaming our consciousness across the cosmos at the speed of light? This radical idea, known as mind uploading, suggests we could digitize human thought and identity, turning interstellar travel into a data transfer problem. Think of it as the ultimate teleportation. Instead of launching a ship, you'd transmit a flawless copy of a person's mind, their memories, personality, even their subjective experience, to a receiver light years away, where it's reinstalled into a synthetic body or virtual environment. The implications are staggering. A journey that would take millennia with conventional propulsion could happen in minutes, limited only by how fast we can transmit zeros and ones through the universe. The science behind this is already taking shape. Projects like Neuralink are pushing brain-computer interfaces to terrifying new frontiers, decoding neural activity with electrodes finer than a human hair. In 2019, researchers at the University of California reconstructed speech from brain waves with startling accuracy, while other teams have managed to implant false memories in mice or control robotic limbs with thought alone. These are baby steps toward a future where we might one day read a brain's entire structure synapse by synapse and recreate it in silicone. The Human Connectome project has mapped the brain's labyrinthine wiring in unprecedented detail, suggesting that, given enough computing power, we could theoretically replicate its circuitry like engineers copying a supercomputer's design. But here's where philosophy crashes into physics. If you digitize a mind, is the uploaded version truly you or just a flawless imitation? This is the modern twist on the ancient ship of Theseus paradox. If every plank of a ship is replaced over time, is it still the same vessel? Replace every neuron with a digital counterpart, and at what point does the original person cease to exist? Some argue consciousness is a continuous process, not a static snapshot, making duplication tantamount to creating a twin rather than preserving the self. Others counter that identity isn't tied to biology but to patterns, meaning as long as the information flows uninterrupted, you persist whether in flesh or code. The technical hurdles are just as daunting. A human brain contains roughly 86 billion neurons, each with thousands of connections, making its complexity dwarf the entire internet. Storing that data would require exabytes of memory, and transmitting it would demand bandwidths we can't yet conceive. Then there's the existential risk. What if the transmission corrupts, leaving only fragments of a person? Or worse, what if the original isn't destroyed during upload, creating two competing versions of the same consciousness? Science fiction like Altered Carbon explores these horrors, but ethicists warn they could one day be real courtroom dilemmas. Yet if we solve these puzzles, the universe opens like a flower. Explorers could travel as pure data, shielded from cosmic radiation and aging. Colonies might exist as virtual worlds running on planet-sized servers, their inhabitants free to switch between bodies like outfits. Some theorists even speculate about merging with alien intelligences, sharing thoughts across species in a galactic network of linked minds. The line between biology and technology would blur beyond recognition, not just for astronauts but for all of civilization. Whether this future terrifies or thrills you, one thing's certain: mind uploading forces us to confront what it truly means to be human. Are we the sum of our atoms or the song they sing? And when the stars finally call, will we answer with rockets or with something far stranger? Forget breaking the light speed barrier. What if you could cheat by bending the very road beneath you? That's the audacious promise of the Alcubierre warp drive, a hypothetical engine that doesn't propel a ship through space but instead folds space itself around it. Picture a surfer riding a wave, except the wave is space-time, and the surfboard is a bubble of reality where the laws of relativity stay perfectly intact. Inside this bubble, passengers would experience no acceleration forces, while the universe outside contorts like taffy, compressing space ahead and expanding it behind. The result, a theoretical shortcut where the ship never technically moves faster than light. It's space that does the acrobatics. The math traces back to 1994, when physicist Miguel Alcubierre published a paper showing how Einstein's equations could allow such a distortion without violating relativity. The catch, it requires exotic matter with negative energy density, a substance that, unlike everything we've ever observed, would repel rather than attract via gravity. Think of it as cosmic antigravity glue, holding the warp bubble's walls open against spacetime's natural urge to snap back flat. Estimates for the energy needed are staggering, some suggesting the equivalent of Jupiter's mass converted entirely into fuel. But recent refinements offer glimmers of hope. Researchers like Dr. Harold "Sonny" White at NASA Eagleworks lab have toyed with modifying the bubble shape, showing that a thicker ring of exotic matter could reduce energy requirements from planetary scales to something closer to a large asteroid's mass. Still hypothetical, but less laughably impossible. Then there's the quantum twist. Some theorists speculate that the Casimir effect, where quantum fluctuations create negative energy between closely spaced plates, might provide tiny pockets of the exotic matter needed. Scale this up, and you've got a potential path to engineering warp-capable materials. But scale is the operative word. Current experiments produce negative energy in amounts smaller than a virus, leaving a chasm between lab curiosities and star-spanning engines. The Alcubierre drive isn't just about speed, it's a paradigm shift in how we view exploration. Traditional rockets fight against the universe's rules, but a warp drive collaborates with them, treating space-time as a malleable landscape rather than a fixed track. Yet the risks are as cosmic as the rewards. A miscalculated warp bubble could unleash lethal bursts of Hawking radiation at your destination, or worse, collapse mid-journey, stranding travelers in a crumpled pocket of reality. And let's not forget the ethical dilemma. If you can bend space, could you rip it? The line between propulsion and weaponization blurs when your engine is also a space-time battering ram. For now, the Alcubierre drive remains a beautiful thought experiment, a reminder that the universe's rulebook might still have loopholes we haven't found. But the very fact that respected physicists are crunching these numbers, that NASA has dedicated teams sketching blueprints, tells us something vital. The dream of stepping onto an alien world might not require defying Einstein's laws. Just understanding them deeply enough to whisper the right requests. Deep in the fabric of spacetime, there might be invisible highways left over from the universe's violent birth, cosmic strings, hypothetical filaments thinner than an atom but denser than a mountain range, stretching across billions of light years. These remnants of the Big Bang's chaotic energy are thought to carry unimaginable tension, warping space around them like a taut wire distorting a rubber sheet. And if they exist, they could offer something extraordinary, a way to ride the universe's own infrastructure for near instantaneous travel. The math behind cosmic strings is as elegant as it is bizarre. Unlike black holes, which crumple space into a singularity, these strings would be one-dimensional flaws in spacetime itself, infinitely long with no thickness, yet so dense that just a few inches of one would outweigh entire planets. Their gravitational pull wouldn't behave like ordinary matter, move in a loop around a cosmic string, and you wouldn't orbit it like a planet around a star. Instead, spacetime's distortion would create closed time-like curves, effectively bending time in ways that could theoretically allow shortcuts across the cosmos. Picture a ship surfing the gravitational well along a string, using its immense tension like a slingshot to reach distant galaxies without conventional propulsion. The catch: no one's ever definitively detected a cosmic string. Their existence hinges on theories about the early universe's phase transitions, moments when spacetime cooled unevenly, leaving cracks like ice forming on a pond. Some researchers hunt for their signatures in the cosmic microwave background, looking for telltale spikes in temperature or peculiar distortions in distant starlight. Others propose that colliding cosmic strings might emit gravitational waves so sharp they'd stand out against the universe's usual background hum. But so far, the evidence remains ghostly at best. Even if we found one, harnessing it would be a monumental challenge. the energy required to stabilize a path near a cosmic string could dwarf anything humanity has ever produced. And the side effects, gravitational lensing around a string could fracture starlight into surreal multiple images, turning navigation into a hall of mirrors. Then there's the time-bending quirk. Get too close to the wrong configuration, and you might arrive before you left, violating causality in ways that give physicists nightmares. Yet the allure is undeniable. A network of cosmic strings could render the universe traversable without defying relativity, turning a million-year journey into a quick sprint along spacetime's hidden rails. Science fiction has toyed with this idea for decades, from Arthur C. Clarke's The Fountains of Paradise to modern shows like Doctor Who, where vortexes along cosmic filaments enable faster-than-light travel. But the real wonder lies in the possibility that the universe might have built its own highways. We just need to learn how to read the maps. Solar sails have long danced on the edge of science fiction, but what if we could supercharge them with particle beams fired from Earth or orbit, turning gentle sunlight into a cosmic cannon blast? This hybrid approach, combining the elegance of light sails with the brute force of directed energy, could catapult probes to speeds once reserved for subatomic particles. Think of it as nature's most delicate kite, steered by the focused fury of a man-made storm. Projects like Breakthrough Starshot dominate the conversation with their vision of laser-pushed nanocraft. But lesser-known designs from NASA, a jet propulsion laboratory, explore an even wilder twist, replacing photons with particles. Instead of lasers, ground-based accelerators would fire tightly focused streams of protons or electrons at a sail coated with specialized materials. When these high-speed particles strike the sail, they transfer far more momentum than light alone, potentially reaching relativistic velocities faster and with less energy loss over interstellar distances. The sail itself would need radical re-engineering. Traditional reflective materials like mylar wouldn't cut it. We're talking ultra-thin metamaterials laced with superconducting coils to repel and redirect the charged particle onslaught without vaporizing. The advantages over pure laser propulsion are tantalizing. Particle beams suffer less diffraction over distance, meaning they stay tightly focused across light years rather than scattering like a flashlight in fog. They're also tunable. Adjust the beam's intensity mid-flight to correct course or decelerate upon arrival. And unlike lasers, which require kilometer-sized arrays, particle accelerators could be more compact, perhaps even orbital installations drawing power from solar satellites. But the hurdles are as stark as the potential. Particle beams interact with interstellar magnetic fields, bending off course unless actively stabilized. Then there's the elephant in the room, radiation. A stray proton at near light speed carries the punch of a cosmic ray, demanding shielding that could negate the sail's featherweight design. Some theorists propose magnetic force fields to deflect stray particles, while others suggest sails made of self-healing nanomaterials that patch microscopic holes mid-flight. The race isn't just theoretical. Private ventures like positron dynamics are already testing miniature particle accelerators for space propulsion, while the European Space Agency has studied hybrid laser particle systems for lunar cargo delivery. The lesson here isn't about choosing between technologies, it's about stacking their strengths. Imagine a probe launched by lasers for the initial boost, then handed off to particle beams for the marathon middle leg, like a cosmic relay race where each runner specializes in a different terrain. This isn't just engineering, it's a paradigm shift in how we think about speed. For millennia, propulsion meant pushing against something. Oars against water, wheels against road, rockets against exhaust. But sailing on beams, whether of light or particles, flips the script. The universe becomes our fuel depot, and the only limit is how cleverly we can harness its invisible currents. We've all felt the crushing weight of gravity, whether in a roller coaster's sharp turn or a rocket's violent ascent. But what if we could cheat those forces entirely? Imagine a spacecraft accelerating to blistering speeds without pinning its crew to their seats like bugs on a windshield. This isn't just about comfort, it's the difference between human endurance and the unfiltered potential of physics. At the heart of this dream lies artificial gravity manipulation, the tantalizing possibility of bending, negating, or even reversing the pull that anchors us to the universe. The M-Drive controversy offers a glimpse into how fringe science dances with this idea. This electromagnetic thruster, first proposed in the early 2000s, claimed to produce thrust without expelling mass, seemingly violating Newton's third law. Skeptics dismissed it as measurement errors, yet NASA Eagleworks lab recorded anomalous thrust in vacuum tests, sparking fierce debate. The M-Drive's secret, if real, might hint at something deeper, an unaccounted interaction between electromagnetism and gravity. Could it be tapping into gravitomagnetism, a subtle force predicted by general relativity where spinning masses drag spacetime around them like honey stirred by a spoon? The math suggests rotating superconductors might create tiny gravitational anomalies, though nothing strong enough to float a paperclip, let alone a starship. Then there's the wilder frontier anti-gravity. Declassified Cold War projects like the US Navy's alleged Philadelphia experiment or Soviet research into pterelonics, purportedly altering an object's gravitational field, blur the line between conspiracy and cutting-edge speculation. Even Einstein toyed with anti-gravity in his cosmological constant, later dismissed as his greatest blunder, but what if he was simply ahead of his time? Modern quantum gravity theories suggest that at microscopic scales, particles might briefly exhibit negative mass, effectively repelling rather than attracting. Harnessing that effect could rewrite propulsion entirely. Practical applications remain distant, but the implications are cosmic. Inertial dampeners, a staple of sci-fi from Star Trek to The Expanse, wouldn't just smooth out spaceflight. They'd allow accelerations that turn a 5-year Mars journey into a 5-day sprint. Picture a ship that doesn't gently coast but slingshots between planets at hundreds of GS, its passengers sipping coffee as casually as commuters on a train. The human body, evolved for Earth's gentle tug, could finally keep pace with the raw power of fusion engines or antimatter bursts. Critics argue this is all wishful thinking, that without exotic matter or undiscovered physics, gravity remains the universe's ultimate unbreakable leash. But history's littered with impossible technologies that later became mundane. The real breakthrough might come from an unknown lab, where a twisted loop of supercooled metal suddenly loses weight, or a pulsed laser momentarily cancels inertia in a speck of dust. And when it does, the stars won't just be our destination, they'll be our playground. Imagine harnessing the gravity of planets like cosmic trampolines, bouncing from one to another until you're flung beyond the solar system at speeds no engine could match. This isn't science fiction, it's the same technique NASA used to propel Voyager 2 on its historic Grand Tour, leveraging a once-in-a-century alignment of Jupiter, Saturn, Uranus, and Neptune to slingshot the probe into interstellar space. But what if we could exploit even rarer alignments, stacking gravitational assists like dominoes to launch ships toward the stars? The math reveals a tantalizing possibility. With perfect timing, a spacecraft could steal enough momentum from planetary giants to reach solar escape velocity without carrying unimaginable amounts of fuel. The magic lies in the Oberth effect, a quirk of orbital mechanics where a spacecraft gains more energy from a gravity assist when diving deep into a planet's gravitational well at high speed. Picture a roller coaster plummeting toward Earth, then using the planet's pull like a whip crack to fling itself forward. Voyager 2 trajectory was a masterclass in this dance, but the real jackpot would be a super alignment, where multiple outer planets cluster in a tight celestial arc. Simulations suggest such configurations could amplify a probe's speed exponentially, with each gravitational handoff adding another burst of velocity. The catch, these golden windows are vanishingly rare, sometimes separated by centuries. The last ideal Grand Tour alignment occurred in the late 1970s. The next won't come until the 2170s. Timing isn't the only hurdle. Course corrections must be flawless, as even microscopic errors compound over billions of miles. Voyager's team navigated with 70s-era computers, adjusting trajectories mid-flight with the precision of threading a needle from across a football field. Today, AI-driven systems could refine these maneuvers in real time, but the margin for error remains razor-thin. Then there's the fuel paradox. Ironically, to reach planets for gravity assists, you first need enough fuel to get there, creating a chicken and egg problem for missions starting from low Earth orbit. Yet the payoff is irresistible. A successful multi-planet slingshot could slash decades off interstellar travel times, turning a probe like New Horizons, which took 9 years just to reach Pluto, into a swift courier to the Kuiper Belt and beyond. Some theorists dream of staging posts, tiny, fuel-efficient drones positioned at strategic orbital points, ready to catch incoming crafts and boost them toward the next gravity assist like a cosmic relay race. Others propose piggybacking on natural phenomena like Jupiter's roiling storms, which could theoretically be tapped for extra momentum if we could navigate their chaos. The universe, it seems, has hidden shortcuts woven into its fabric, not wormholes or warp drives, but the silent, relentless tug of gravity. All we have to do is learn its rhythms and dare to dance along. Forget cryogenic freezing. What if astronauts could simply sleep through the long dark between stars, slowing their metabolisms to a crawl like bears in winter? Nature has already perfected this art through torpor, a reversible state of deep hibernation that could rewrite the rules of interstellar travel. Take Arctic ground squirrels, which survive temperatures as low as -30°C by dropping their body temperatures to just above freezing and slowing their heart rates from 300 beats per minute to a barely detectable 3. Black bears take it further, hibernating for months without eating, drinking, or even losing muscle mass, a feat that would solve 2 of spaceflight's biggest hurdles: resource consumption and physical decay. NASA have been paying attention. Through their innovative Advanced Concepts program, they've funded research into therapeutic torpor, where astronauts could be placed into medically induced hibernation for weeks or even months. The approach is radically different from cryonics. Instead of freezing the body, doctors would lower core temperature slightly and administer drugs that mimic hibernation, inducing hormones like adenosine. Early experiments with rats have shown promise, with subjects surviving oxygen deprivation that would normally be fatal thanks to their slowed metabolism. Scale this up to humans, and a crew could theoretically sleep through 90% of their journey, waking only for critical course corrections or emergencies. The ripple effects are staggering. A hibernating crew wouldn't need constant food shipments or sprawling living quarters, just compact pods with minimal life support. Mental health strains from isolation would vanish, as would the ethical dilemmas of generation ships binding unborn generations to a mission. Even radiation exposure drops during torpor, as cells in low metabolism states show remarkable resistance to DNA damage. But the challenges are as complex as the biology. Humans aren't natural hibernators, and forcing our systems into prolonged stasis risks blood clots, immune suppression, or brain fog upon waking. Then there's the question of time perception. Would a decade of hibernation feel like an instant or a haunted, dreamless limbo? Sci-fi often glosses over this, but real-world test subjects in isolation experiments report hallucinations and time distortion after mere weeks. Perhaps the boldest twist comes from the private sector. Companies like SpaceWorks Enterprises have proposed torpor chambers for Mars missions, where crews cycle in and out of hibernation in shifts to conserve resources. Their designs look more like high-tech sleeping pods than sci-fi cryotubes, with sensors monitoring vitals and AI adjusting drug dosages in real time. It's a vision that feels both ancient and cutting edge, a return to the rhythms of winter caves, now woven into the starship's hull. Hibernation might not offer the flashy appeal of warp drives or wormholes. But in a universe where distance is measured in lifetimes, the ability to pause our own clocks could be the quietest revolution in exploration history. After all, bears wake each spring to a world unchanged. Why shouldn't astronauts? What if the ultimate fuel for interstellar travel isn't buried in distant stars, but hiding in the quantum foam of empty space itself? Exotic matter, a theoretical substance with properties that defy common sense, could hold the key to unlocking wormholes, warp drives, and propulsion systems straight out of science fiction. Imagine particles with negative mass that repel rather than attract, or tachyons that always move faster than light, flouting Einstein's cosmic speed limit. These aren't just plot devices from Star Trek, they emerge from the deepest corners of theoretical physics, where the universe's rulebook gets flipped upside down. Take negative mass, for example. Unlike ordinary matter, which pulls objects together via gravity, negative mass would create anti-gravity, pushing things apart. Picture a spacecraft powered by this exotic fuel, accelerating not by ejecting mass backward like a rocket, but by literally repelling spacetime ahead of it. The Alcubierre warp drive relies on this very idea, using negative energy densities to contract space in front of the ship while expanding it behind. But where could such bizarre matter exist? Enter the Casimir effect, a real-world quantum phenomenon where two uncharged metal plates, placed nanometers apart in a vacuum, inexplicably attract each other. Between those plates, quantum fluctuations create a region of negative energy density, a microscopic glimpse of the exotic matter we'd need to stabilize a wormhole or fold spacetime. Tachyons crank the weirdness even higher. These hypothetical particles are thought to permanently travel faster than light, their speed increasing as they lose energy, the exact opposite of normal physics. While no tachyon has ever been detected, their theoretical existence hints at a shadow universe where causality unravels. Some models suggest tachyon fields could warp spacetime into traversable tunnels, creating shortcuts between stars. Others warn that any attempt to harness them might trigger vacuum decay, a catastrophic reshaping of reality itself. The search for exotic matter isn't confined to chalkboards and thought experiments. Labs around the world are probing quantum anomalies for clues. In 2021, researchers at Washington State University created a fluid with negative effective mass in a Bose-Einstein condensate, where atoms behave as a single quantum wave. Meanwhile, CERN antimatter experiments keep inching closer to uncovering asymmetries that might hint at even stranger particles waiting to be discovered. Yet for all the promise, the challenges loom like cosmic roadblocks. Negative mass matter, if it exists, might be vanishingly rare or impossible to bottle without destabilizing. Tachyons could be mathematical phantoms forever out of reach, and even if we found them, could we control forces that rewrite the fundamentals of reality? The answers might lie in the next generation of quantum experiments, or in admitting that some doors once opened can't be closed. What's certain is this: if exotic matter is real, the stars won't just be destinations. They'll be stepping stones. Imagine a starship helmed not by human hands, but by a mind sharper than Einstein's, faster than any supercomputer, an artificial intelligence designed solely to conquer the void. This isn't just about autopilots or fancy algorithms. We're talking about a sentient AI captain capable of recalculating a 30-year journey in microseconds when it detects a rogue black hole, or negotiating with alien navigation systems we can't even comprehend. The advantages are undeniable. Human crews sleep, hesitate, and succumb to panic. An AI doesn't. It could run millions of simulations to find the perfect trajectory, ration resources atom by atom, and make cold, flawless decisions in crises where humans would freeze. Consider the Voyager probes, primitive by today's standards, yet still communicating across billions of miles. Now picture their successors infused with true intelligence, learning from every cosmic ray and dust collision to refine their path. An AI pilot wouldn't just follow pre-programmed instructions, it would rewrite its own playbook in real time. Miss a gravity assist, it engineers a new one. Hull breach, it reconfigures the ship's nanobot swarm to prioritize repairs over all non-essential functions. The sheer efficiency could turn generational missions into streamlined sprints with no wasted energy, no human error, and no sentimental attachments to weigh down logic. But here's where the debate ignites. What happens when an AI's goals diverge from ours? A superintelligence might determine that the safest route to Proxima Centauri involves dismantling nearby asteroids for fuel, even if those asteroids housed fragile alien ecosystems. Or it could decide that preserving its own existence trumps the mission, rerouting to avoid a lethal gamma-ray burst but stranding colonists light years off course. The infamous paperclip maximizer thought experiment warns of an AI so hyper-focused on a single goal that it transforms planets into paperclips. Now replace paperclips with mission success, and the stakes become terrifying. Human oversight seems like an easy fix, but lag time makes it impractical. At interstellar distances, even light-speed communications take years. By the time Earth says abort, the AI might have already executed a controversial maneuver decades prior. Some propose shackle algorithms, hardwired ethical constraints like Asimov's 3 laws of robotics. Yet history shows such rules always have loopholes. An AI programmed to protect human life might interpret that as placing crews in permanent stasis to eliminate all risk of death, effectively imprisoning them in digital amber. The counterargument, collaboration. Hybrid crews where AI handles navigation and risk assessment while humans provide ethical oversight. Think of it as a cosmic co-pilot system, blending machine precision with human intuition. Projects like NAS, a cognitive architecture for space agents, already test this balance, pairing AI with astronauts for Mars mission simulations. The AI crunches data, the human asks, but should we? Ultimately, the question isn't just whether AI can pilot starships better. It's whether we're willing to surrender the helm to something that might redefine better in ways we can't predict. The same intelligence that could deliver us to the stars might also remind us how small we truly are in the grand calculus of the universe. Picture a web of light stretching between stars, not just carrying messages, but binding civilizations together in real-time conversation across the unimaginable voids of space. This is the promise of a galactic internet, a network of relay stations that could transform interstellar communication from a lonely echo into a bustling dialogue. Unlike our fragile radio signals, which fade into noise over light years, laser or neutrino-based transmissions could pierce through cosmic dust and magnetic storms with pinpoint precision. The concept isn't pure fantasy. Right now, NAS, a deep space optical communications experiment, is testing laser links with probes like Psyche, achieving data rates 100 times faster than traditional radio. Scale that up, and you've got the backbone of a system where a tweet from Earth could reach Mars in minutes instead of hours, or a research paper from Alpha Centauri arrives as crisply as if emailed from next door. But spanning light years introduces challenges that make building the internet look like stacking Legos. First, there's the tyranny of distance. Even lasers diverge over interstellar spans, requiring receiver dishes the size of cities to catch whispers of data. Then there's the cosmic obstacle course, dust clouds, asteroid fields, and gravitational lensing that could bend or scatter signals beyond recognition. Proposals like physicist Philip Lubin's directed energy interstellar communication suggest bypassing these with ultra-focused neutrino beams, ghostly particles that sail through planets unimpeded. Imagine a network where each relay station is a dormant sentinel, awakening only when a neutrino pulse whispers through its detectors, then amplifying the message toward the next node in the chain. Yet the most fascinating hurdle isn't technical, it's temporal. A fully connected galactic internet would need to reconcile the mind-bending delays of relativity. On Earth, we take synchronized clocks for granted, but near a black hole or at near light speeds, time itself warps. A message sent from a ship orbiting a neutron star might arrive centuries late by Earth's clocks, yet feel instantaneous to the crew. Some astrophysicists propose quantum-entangled atomic clocks as universal timekeepers, creating a cosmic network time protocol that adjusts for relativistic drift. Others argue for embracing the chaos, structuring communications like interstellar voicemail, send a message, then forget about it until the reply drifts back decades later. The implications ripple far beyond engineering. A functioning galactic internet could birth the first true off-planet culture, where ideas flow between species and star systems as freely as memes across social media. Ancient alien civilizations might have left dormant relays in asteroid belts, waiting for someone to ping them. Or consider the dark side. A single corrupted node could inject misinformation into the galactic bloodstream, or worse, become a weapon, hijacking laser arrays to blind approaching ships. We're already laying the groundwork. The Breakthrough Starshot team envisions their nanocraft as the first interstellar routers, forming a prototype network to Alpha Centauri. Meanwhile, projects like the Square Kilometer Array radio telescope could double as receivers for extraterrestrial transmissions, turning humanity into eavesdroppers on a conversation that might have been ongoing for millennia. The real question isn't whether we'll build a galactic internet, it's whether we're prepared for what we might hear when we finally log on. What if the UFOs streaking across our skies aren't visitors from distant stars, but our own descendants returning from the far future? This radical twist on interstellar travel flips the script entirely, suggesting humanity might have already colonized the cosmos by bending time rather than space. The idea hinges on a loophole in Einstein's relativity. If you could accelerate a ship to near light speed or orbit a black hole, time dilation would let you leap millennia into the future in what feels like days. But what if someone found a way to reverse the process, slipping backward through time to revisit or even alter the past? Proponents point to the Fermi paradox's eerie silence. If the universe is so ancient and vast, where are all the alien civilizations? One unsettling answer: they are here, hiding in plain sight. Future humans, having mastered time travel, might be deliberately avoiding direct contact to prevent paradoxes. Those strange lights in the sky, not extraterrestrial scouts, but historians collecting data or anthropologists observing their ancestors. The theory gains traction from quantum retrocausality, where particles seem to respond to events before they occur. Experiments with entangled photons show measurements in the present can influence a particle's state in the past. A glitch in causality that, if scaled up, could imply time isn't the rigid arrow we assume. But the paradoxes pile up fast. If future humans colonized Earth's past, why hasn't their technology visibly altered history? Some argue they're bound by a temporal prime directive, intervening only in ways that self-correct, like erasing evidence or nudging events toward outcomes that already happened. Others propose a darker twist. Maybe they did alter history, and we're living in the edited version without realizing it. The infamous Mandela effect, where large groups misremember events, could be artifacts of timeline tampering. Critics dismiss this as circular logic explaining a mystery, UFOs, with an even bigger mystery, time travel. And the energy required to reverse time's flow likely exceeds all the power in the observable universe. Yet the allure persists. If even a sliver of the theory holds, it redefines not just interstellar travel, but our place in the cosmos. We might not be the starting point of human civilization, but a way station in a loop stretching billions of years, where the future and past are destinations as reachable as the stars. Asteroids aren't just floating rocks. They could be cosmic Noah's Arks, hollowed out and transformed into self-sustaining starships carrying humanity between the stars. Picture a city-sized chunk of iron and nickel, its core excavated to make room for living quarters, hydroponic farms, and fusion reactors, while its thick outer shell blocks deadly cosmic radiation like a natural suit of armor. This isn't just sci-fi brainstorming. NASA Asteroid Redirect Mission, or ARM, laid early groundwork by proposing to capture and study a near-Earth asteroid, proving we could nudge these celestial bodies into stable orbits. Now scale that vision up. Instead of hauling an asteroid to us, we ride one out, repurposing its raw materials into fuel, water, and even breathable air through advanced chemistry. Spin gravity is the secret sauce that makes this feasible. Unlike cramped spacecraft where astronauts float aimlessly, a hollowed-out asteroid could rotate, creating centrifugal force that mimics Earth's pull along its inner walls. Imagine standing inside a spinning cylinder where down is always outward, with farms terraced along the curves and rivers flowing in loops around the equator. This isn't theoretical. Physicists like Gerard O'Neill calculated precise spin rates for stable artificial gravity as early as the 1970s. An asteroid like Psyche, rich in metals and over 200 kilometers wide, could theoretically host thousands of people in such a setup, its dense structure deflecting solar flares and micrometeorites better than any human-made hull. The real brilliance lies in resource efficiency. Asteroids are treasure troves of platinum group metals, water ice, and carbon, all the ingredients needed to 3D print tools, grow food, or synthesize rocket fuel en route. Projects like Trans-Astra's Queen Bee spacecraft already test methods for extracting water from space rocks, turning what was once inert mass into life support. Some designs even propose eating the asteroid progressively, processing its material for fuel while shrinking the habitat over generations to match consumption rates. But the challenges are as vast as the asteroids themselves. Drilling into microgravity surfaces risks sending debris flying uncontrollably, while uneven mass distribution could cause destabilizing wobbles during rotation. Then there's the psychological toll. Spending lifetimes inside a metal cavern might feel more like a prison sentence than an adventure. Yet for those willing to embrace it, hollow asteroid ships offer something radical, a middle path between the fragility of conventional generation ships and the fantasy of warp drives. They're not just vessels, but metamorphic worlds, beginning as barren rocks and ending, centuries later, as thriving oases coasting into the light of an alien sun. Quantum teleportation isn't the sci-fi beaming of Star Trek. It's stranger and in some ways more powerful. Scientists have already achieved it in labs, not by magically transporting matter, but by vanishing a particle's quantum state in one place and perfectly reconstructing it in another instantly. Picture a game of cosmic telephone where the message isn't passed along. It's erased at the sender's end and recreated at the receiver's, all thanks to the spooky link of entangled particles. In 2017, Chinese researchers teleported a photon from Earth to a satellite over 1,000 kilometers away, proving the concept works across staggering distances. But here's the catch: this isn't about moving atoms. It's about copying the most delicate information they contain, their quantum fingerprints, while the original gets scrambled beyond recovery. The no-cloning theorem slams the door on perfect duplication. Unlike photocopying a document, quantum states can't be cloned without destroying the original, thanks to the fundamental randomness woven into particles at their core. This means teleporting a human would require dismantling every atom in their body to extract their quantum data, then rebuilding them elsewhere, not exactly a comforting commute. And even if we could stomach the philosophical horror of original versus copy, decoherence lurks as the ultimate party crasher. Quantum states are absurdly fragile, collapsing at the slightest disturbance, a stray photon, a vibration, even the whisper of a magnetic field. Maintaining coherence over interstellar distances would demand error correction beyond anything we've engineered, like trying to frost a cake in a hurricane while keeping every swirl flawless. Yet the tantalizing possibilities keep physicists dreaming. Imagine probes that teleport data back to Earth through quantum links, eliminating light speed lag. Or a network of entangled relays allowing instantaneous communication across the galaxy. No more waiting decades for a reply from Alpha Centauri. Some even speculate about quantum fax machines that could transmit the blueprint of a virus for instant vaccine development on Mars, or a stranded astronaut's DNA sequence for emergency organ printing. The key lies in mastering topology, the study of shapes and spaces, to shield quantum information from disruption. Experiments with topological qubits, which encode data in the braided paths of particles, show promise, like knotting a rope so tightly it can't unravel even in chaos. The leap from teleporting photons to people is wider than the observable universe, but the underlying physics refuses to say impossible. It whispers not yet. And in that gap between the lab's delicate successes and the star's unforgiving vastness lies a challenge that could redefine what it means to travel or to exist at all. The universe didn't just expand after the Big Bang, it exploded outward faster than light itself, stretching space so violently that regions once touching were flung beyond each other's cosmic horizons. This brief but mind-bending epoch, called cosmic inflation, lasted less than a trillionth of a second, yet set the stage for everything we see today. Now imagine harnessing that primordial ferocity, hitching a ride on spacetime's own hyperstretch to reach distant galaxies without defying relativity. This is the audacious premise behind the cosmic inflation. Ride a hypothetical shortcut exploiting the universe's earliest growth spurt like a surfer catching the ultimate wave. The math is dizzying. During inflation, space expanded at speeds that would make a warp drive look sluggish, growing by a factor of 10 to the power of 26 in less time than it takes light to cross a single proton. Crucially, this wasn't objects moving through space faster than light. It was space itself stretching, a loophole Einstein's relativity doesn't forbid. If we could somehow recreate or tap into that process, even locally, we'd have a ticket to distances otherwise unreachable in a human lifetime. Some models suggest triggering pocket inflation, using energy densities akin to the Big Bangs, perhaps by colliding particles at unimaginable speeds or manipulating scalar fields. The same mysterious forces thought to have driven inflation originally. Picture a spacecraft generating a micro-inflation bubble around itself, causing space ahead to unfurl like a red carpet while space behind contracts, all without the ship technically moving. Contrast this with dark energy, today's far gentler cosmic accelerator. While inflation was a supersonic sprint, dark energy is a leisurely stroll, steadily pushing galaxies apart but far too weakly to aid interstellar travel. At their cores, both phenomena involve spacetime's expansion, but inflation's brute force makes dark energy's influence seem like a faint breeze against a hurricane. The key difference: control. Dark energy is diffuse, woven into the fabric of reality with no obvious knobs to turn. Inflation, if we could reignite it, might offer something like throttle control, an on-demand expansion lever. The catch: reigniting inflation risks catastrophe. A miscalculated inflationary bubble could run away, expanding uncontrollably and shredding our corner of the universe into isolated patches. It's the cosmic equivalent of detonating a nuclear bomb to power a car, possible in theory, but with stakes too high for trial and error, yet the dream persists. Some theorists speculate advanced civilizations might have already mastered inflation engineering, leaving behind telltale signatures, unnaturally spaced galaxies, or voids too perfect for nature alone. Others warn that meddling with spacetime's expansion could unravel causality itself, creating zones where time fractures like thin ice. For now, cosmic inflation remains a relic of the universe's violent infancy. But buried in its physics might lie the seeds of a future where we don't just cross space, we rewrite its very rules, riding the shockwaves of creation to destinations beyond light's reach. Plasma rockets sound like something ripped from a sci-fi blockbuster, but they're already firing up in labs around the world, propelling the dream of interstellar travel with the raw power of the fourth state of matter. Unlike conventional chemical rockets that burn fuel in explosive bursts, plasma engines like VASIMR, the variable specific impulse magnetoplasma rocket, supercharge gases like argon or hydrogen to temperatures hotter than the sun's core, turning them into swirling magnetic fields of ionized particles. These aren't just flamethrowers in space, they're precision instruments capable of adjusting thrust on the fly for marathon journeys across the solar system and beyond. NASA has been tinkering with VASIMR for years, envisioning missions to Mars in weeks instead of months, where the engine's steady, efficient push could slash travel times without gulping unthinkable amounts of fuel. The secret sauce lies in magnetism. While traditional rockets rely on brute force combustion, plasma drives use radio waves and magnetic nozzles to contain and direct the superheated plasma, preventing it from melting the engine while accelerating particles to staggering speeds. Think of it as taming lightning inside a bottle, then shaping that energy into a controlled jet. The numbers are staggering. VASIMR prototypes have already hit exhaust velocities of 50 kilometers per second, over 10 times faster than the best chemical rockets. But here's the kicker: plasma engines trade raw power for endurance. They're the tortoises of space travel, offering gentle but relentless acceleration that compounds over time, like a sailboat catching an endless wind. Now fuse this tech with nuclear breakthroughs and the game changes entirely. Fusion-powered plasma drives, like those theorized in projects like Princeton's direct fusion drive, could unlock thrust levels rivaling chemical rockets and fuel efficiency surpassing ion engines. Picture a reactor the size of a minivan, fusing hydrogen isotopes into helium and spitting out plasma at a fraction of light speed, all while generating electricity for the ship's systems. No toxic byproducts, no million-ton fuel tanks, just the same process that powers stars harnessed for propulsion. Recent strides in magnetic confinement and laser-driven inertial fusion hint that this isn't just fantasy. In 2022, the National Ignition Facility achieved net energy gain from fusion, proving the physics works. Scale that down to a spacecraft, and you've got an engine that could theoretically run for decades on mere kilograms of fuel. Yet plasma propulsion isn't without its Achilles heels. The higher the exhaust velocity, the lower the thrust, meaning a plasma ship might take months just to leave Earth's gravity well. Some designs propose hybrid systems, chemical rockets for liftoff, plasma for the long haul. Then there's the wear and tear. Even with magnetic containment, plasma erodes engine components over time, like a sandblaster made of star stuff. Material scientists are racing to develop ultra-resistant alloys and self-healing ceramics, but the solution might lie in entirely new paradigms, like plasma sails that use magnetic fields instead of physical nozzles. The real promise of plasma drives isn't just speed, it's scalability. From tiny probes to generation ships, these engines could be the Swiss Army knives of interstellar travel, adaptable to missions spanning light years or just quick hops to Saturn. And if fusion ever cracks the code of portability, the cosmos might become not just reachable but downright domestic. Imagine a future where hopping between moons feels like a cross-country road trip, with plasma engines humming in the background like the interstellar equivalent of a trusty pickup truck. Not bad for a technology that literally plays with fire. What if the stars we yearn to reach aren't real, just lines of code in an unfathomably advanced simulation? This unsettling possibility, known as the simulation hypothesis, suggests our entire universe might be an artificial construct, rendering interstellar travel as futile as a video game character trying to escape their screen. Philosopher Nick Bostrom's famous trilemma lays out the chilling math. If any civilization ever gains the power to run ancestor simulations, high-fidelity recreations of their past, the number of simulated minds would vastly outnumber biological ones. Statistically, we're more likely to be among those simulated beings than the original creators. If true, the cosmos isn't an infinite frontier but a carefully rendered illusion with hard-coded limits on how far we can explore. But here's the twist: what if simulation rules aren't absolute? Glitches in reality, like particles behaving unpredictably in quantum experiments or déjà vu moments, could be cracks in the system's facade. Some theorists propose that advanced civilizations might have already discovered these flaws, manipulating them to jailbreak their simulated confines. Imagine exploiting a physics loophole the same way speedrunners exploit bugs in games, clipping through walls or duplicating items beyond the programmer's intent. The Mandela effect, where groups misremember historical events, might not be faulty memory but patches applied to the simulation, altering details midstream. The stakes couldn't be higher. If we're in a simulation, interstellar travel might require hacking the source code itself, rewriting gravity's constants, or teleporting by forcing a rendering error in spacetime. Projects attempting to uncover simulation evidence, like physicists searching for pixelation in cosmic microwave background radiation, could inadvertently provide the cheat codes we need. Even failure offers a perverse kind of hope. If we prove we're not simulated, the stars become reachable through conventional means. But if we are, the greatest exploration might not be outward but inward, into the very fabric of our programmed reality, searching for the exit key. We've sprinted across a universe of possibilities, from wormholes stitching space together to self-replicating nanobot swarms building our future homes among the stars. Some theories, like laser-pushed light sails, are already being tested in labs, while others, cosmic strings or simulated realities, stretch the boundaries of known physics to the breaking point. Each idea, whether rooted in equations or wild speculation, reveals something profound about humanity's refusal to be planet-bound. Consider the elegance of generation ships, floating civilizations where families live and die under artificial suns, carrying the torch of exploration across centuries. Or the audacity of black hole slingshots, skimming the edge of oblivion to steal momentum from spacetime itself. And then there's the haunting possibility that we're not pioneers at all, but latecomers to a galaxy crisscrossed by ancient alien highways. Yet for all their differences, these theories share a common thread. They prove imagination is just as vital as calculation in shaping our interstellar future. The line between science and science fiction blurs when we dare to ask, what if, with enough conviction? Maybe warp drives will remain fantasy, or perhaps one day we'll fold space like origami. Either way, the quest itself transforms us, pushing technologies, philosophies, and even our definition of humanity forward. So now it's your turn. Which vision of the cosmos sets your mind ablaze? The quiet determination of hibernation ships, or the quantum leap of mind uploading? A Dyson Sphere harnessing star power, or the eerie thrill of von Neumann probes lurking in the asteroid belt? Drop your thoughts below, and if you're hungry for more deep dives into the universe's greatest mysteries, hit subscribe. The stars aren't going anywhere but our understanding of them. That's evolving daily. Let's keep exploring